The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you. Thank you, Anna, for introducing the session. A very good day to everyone, and thank you for joining us. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Shexiu Huang from ITU, the International Telecommunication Union. Today, we're excited to host another interesting talk titled Enhancing NextG with ML-based Multi-User Resource Scheduling. Today, we'll delve into the complexities of managing multiple users in massive MIMO networks and explore how machine learning can provide efficient solutions to optimize spectral efficiency and fairness. The webinar aims to explore the challenges associated with multi-user beamforming scheduling in massive MIMO systems and present machine learning-based solutions to address these challenges. By fostering innovation and collaboration among participants, the webinar seeks to facilitate the development of robust scheduling algorithms that can effectively manage multiple users in dynamic network environments. Additionally, the webinar will provide insights into the available datasets and evaluation criteria for the challenge, with the ultimate goal of advancing the field of multi-user scheduling in massive MIMO systems to maximize network throughput and fairness. As always, we are counting on you to help create an engaging discussion. If you have any questions, please type them on the video wall and we will take them during the Q&A session right after the talk. Before officially kicking off the session, I would like to introduce our esteemed speakers. Ashutosh Sahaval, who is a professor and chair in the Department of Electrical and Computer Engineering at Rice University. He works in two independent areas, wireless networks and digital health. His recent work in wireless focuses on joint wireless communications and imaging and large-scale experimental platforms. He leads the Rice Renew project. And Rahman Dus Mohammadi. He is an assistant research professor in the Department of Electrical and Computer Engineering at Rice University. His work focuses on the design and efficient implementation of next-generation wireless network systems. He is the technical lead for the Rice Renew project. And last but not least, our speaker, Santiago Segarra. Santiago Segarra is an associate professor in the Department of Electrical and Computer Engineering at Rice University. His research interests include network theory, data analysis, machine learning, and graph signal processing. And my colleague Vishnu, who will be taking charge of the Q&A session. Without further ado, I would like to give the floor to Mr. Ashutosh. Thank you.
Excellent. Thanks for the introduction, Sheshu. We can get started. Rahman, if you can. Yeah, thank you. So first of all, thanks for the invitation to host this competition, and it's been a pleasure so far. I'm looking forward to the remaining competition. For all those who are joining from all over the world, we are from Rice University and work on wireless communication systems, especially designing next generation systems. In this competition, we are going to focus on a really important problem in massive MIMO systems, which are the current standard in wireless systems, which is that of resource allocation. So the agenda for the day is I'll give a very brief, super brief background on what is massive MIMO, and then talk a little bit about the Rice systems and the history of where these data sets for these competitions are coming from. Santiago will talk a little bit about machine learning in wireless, and then Rahman will take us through the problem statement and the rest of the presentation. So briefly, massive MIMO relates to the use of many antennas at the infrastructure nodes like base stations. So we already know that as the number of antennas grows, the spectral efficiency of the system, how many bits per unit time we can push through, increases. And the increase also comes from by using the diversity in the fading channels. And this allows us to push more data in the same resources. In the massive MIMO system, in the next slide, we can see that we have a large number of degrees of freedom. And what we use those are for doing what is called multi-user beamforming. We can actually send data simultaneously to many more users than the previous generation systems, which leads to significant increase in capacity. And in fact, it simplifies interference management across cells. And this is basically one of the main reasons why it has been adopted as a 5G technology and will continue to be a staple technology in the next generation systems. At Rice, we have been working for many years now on enabling our community to do research. So not only we build systems and for ourselves, we have the culture here of open sourcing and making things available for the wider community. On the hardware side, many years ago, we built one of the first multiple antenna software-defined radio, which was then actually available to the broader community and used by many folks over the years. That platform allowed us to demonstrate the first ever massive MIMO base station design, a practical design, which had a multi-user beamforming capabilities, and that platform was called Argos. Argos became the basis for the Rice Renew platform, which is one of the several NSF power platform available to the wider community. It's the world's first multi-cell testbed, which is completely software defined and uses these base stations, which are now commercially available. And in fact, the public deployment of this station, this testbed is now available for access for any researcher at University of Utah as a part of the powder testbed. Using these systems and continuing with our desire to support the whole community, we have been regularly releasing very novel and diverse open data sets using this platform. And till date, we have released around 11 data sets with which take around 6.5 terabytes of storage, and many more are on the way. And the current competition is based on some of the data sets which we have already released to the community. So with that, I'm going to hand it to my colleague, Santiago Segura, to talk about the role of machine learning in wireless communication systems.
Awesome. Thank you, Ashu. Thank you all for joining, and thanks a lot to the organizers for putting this together. Indeed, I'm Santiago Segura, also from Rice, and I come to this, joint collaboration more from the ML side. And indeed, this data challenge falls into the broad umbrella of what we can call machine learning for wireless networks, which is certainly a hot area. Maybe no one is convincing of that, but it's always good to look at a few numbers. So this is an included dynamic field. So, a very simple experiment that anyone can do. Just go to Google Scholar, and then you look for the exact matching of machine learning plus wireless networks over the years. And then you check, how many papers fall into that category. And here we see an increasing trend, right? From, say 2016, where there were like 3,000 or so papers, to 2022, that we're on the verge of 20,000. And this clear trend hides maybe some sub-trends within them, right? And one that is clearly growing, we go to the next slide, please, is the notion of deep reinforcement learning, right? So if you do the same experiment with DRL plus wireless networks, then we can see that in 2016, there were 20 papers or so. When in 2022, we have over 5,000 papers that mentioned, and of course, this is a proxy for actually working on this, right? But the papers that at least mention deep reinforcement learning and wireless networks together. And this is very relevant because the baseline of today that Raman will be discussing falls under this category. Next slide, please. Yeah, so in any case, machine learning in wireless have been applied to many, many different problems across the different networking layers. Not only the problem that we'll be discussing today, but power allocation and beamforming, spectrum allocation and sharing, cache management, link scheduling, user association, base station switching, routing, you name it. All the way from the physical layer and up, people have applied machine learning and different tools within machine learning in order to try to solve this problem. And things like 6G, for example, the idea is that AI will be a big enabler into this new generation of cellular communications. Go to the next slide, please. And indeed, we, as a team, at RISE, and many of us involved in there, we have worked in many of these problems beyond the one that we'll be discussing today. So here, just to give you a very small sample, on the physical layer, we worked on beamforming. There are some publications listed, but indeed that, and some of the, bullet point results that we have achieved. We go to link scheduling, also increasing throughput by a big margin. In the networking layer, we have worked on routing. And the key thing, at least to me, is this line in the bottom that we can tackle many of these problems separately, and indeed one of these problems will be tackled through this data competition, but there is room for compounding effects by combining all these machine layer learning applications across the different layers. So this is a good kind of high-level picture to keep in mind of how today's data competition would fall under this bigger umbrella. With this, I pass it back to Raman. Thanks.
Thank you, Santiago. Thank you, Ashu. And thank you, AI for Good, for helping organizing this challenge. My name is Rahman Dus Mohammadi, and I'm going to actually go to the rest of the slides. Particularly, I'm going to talk about problem statement for this challenge. So let me start with giving a very brief background on essentially beamforming process in a massive MIMO network. So let's say, considering an uplink signal model, what a base station actually receives across the antennas can be shown with a vector Y here, M by 1 vector, where M is essentially the number of antennas. And then we deal with essentially a channel matrix, right, which is essentially an M by K channel matrix, with K being the number of users that are actually transmitting a vector X, essentially. Vector X would be the vector of transmitted symbols, and then N being the additive noise here. And essentially, considering a very common beamforming algorithm called zero forcing, the beamformer essentially calculates a pseudo inverse of the estimated channel, or H hat here, and then use this beamformer to essentially multiply by the receive vector, and then essentially estimate the transmitted symbols as X hat. Using this X hat, we can essentially calculate an achievable rate, a upper bound achievable rate using the Shannon formula, which is a log of 1 plus SINR. And SINR here will be essentially a function of x hat and x, and how close the estimated symbols are to the actual transmitted symbols. So this is the background for the beamforming. And then one challenge in essentially beamforming is that if the channels of different users are correlated to each other, as for example, what we see in this plot here, where the channels gains of two users or UEs in 5G terminology are shown across frequency. If these channels are actually correlated, then the channel matrix H will be ill-conditioned in mathematical terms, which leads to essentially high inter-user interference among these users that are simultaneously transmitting, which leads to low SINR and low achievable rate that we've just discussed. So essentially, we need to carefully schedule users that are being beamformed or transmitting for transmitting to the base station to make sure that we get maximal rates out of the system. So that brings me to the formal statement of the problem in this challenge, which is essentially for resources scheduling. And that means that we would like to schedule time, frequency, and spatial resources to users to maximize rate and fairness. So for example, we can see this example here where the base station can actually beamform to user 1, 3, and 4 in the time interval of n, and then the next time interval it can pick essentially another set of users 2, 3, and 5 to transmit to. So we can mathematically formulate this problem as an optimization problem here, where essentially the goal is to find the let's say the matrix X, which is essentially made up of these X, B of L parameters, so that essentially we maximize this whole term, which is the sum rate of the whole system. And this U is essentially what we call a proportional fair rate, right? So essentially, it's the instantaneous rate that is achieved by letting the user L to transmit at, let's say, subcarrier or frequency B, but normalized with the total sum of the rates that it has, that particular user has gotten in the previous time transmission time intervals. So this is actually traditionally called a proportional fair scheduling algorithm that in this case applied to massive MIMO networks. So for example, here you can actually see an example of how these matrix X or vector X's are being formed here. So in general, we actually shoot for 3 design metrics here. One is the sum rates. So that means that how much in total rate we get out of the network by transmitting to different users in the network across frequency at different times. And also the fairness, right? So how fair we are to different users given different channels that they're experiencing. And then lastly, we care about computational complexity a lot, as we discussed in a little bit. So for example, if we want to consider the optimal algorithms, the one that we just talked about, or a variation of it, which is actually just maximizing the sum rate, these are provably NP-hard problems, which have very high computational complexity, and they're not really scalable to large networks with large number of users, in particularly for massive MIMO networks, which are expected to have serving a lot of users. And then there are a lot of heuristic algorithms out there that are typically very suboptimal, either in the amount of rate that they can achieve, or the fairness that they can provide to users, or both metrics. So the question that we ask here is that can we hit all these 3 goals through machine learning algorithms? And that brings me to our baseline solution here, which is based on this recent paper that was published in the IEEE transaction on machine learning in wireless, machine learning in communication and networking. And this paper essentially provides a solution based on deep reinforcement learning, or DRL, and in particular based on a well-known model called soft actor critic, which actually shows good exploration property as well as good scalability features. And in particular, for designing this DRL, a reward function is considered, where this reward function is a combination of the rate that the network is actually getting, right? So it goes back to the formula that we proposed earlier, we showed earlier, summing over all the rates across users and subcarriers, and this final value is essentially normalized, as well as another fairness parameter called shown as f of t here, which is based on a very well-known Jaynes fairness index that is calculated with this formula. Using this DRL model that we just talked about, so essentially we can show results for relatively large networks, let's say in this case 64 antenna base station with 64 users, and the results show that this particular solution can actually beat the approximate proportional fairness algorithm by 2x, and providing at the same time high fairness values in highly mobile scenarios. And additionally, in terms of computational complexity, we can show that essentially this solution can achieve 20 times better a runtime than essentially the approximate proportional fairness, and also provide almost 2 times better runtime compared to other deep reinforcement learning algorithms. So let's look at the resources for this challenge. So as part of this challenge, we will provide 2 data sets. The first data set is essentially derived from one of the Renew data sets that Ashu talked about earlier. So in this data set, a 64 antenna base station was used on Rice campus. In this, you see the map of the measurement here. And essentially, the users were put in different clusters of 4 line-of-sight clusters and 5 non-line-of-sight clusters. We have essentially created the derivation of this data set where there are 64 users in the data set transmitting across 52 subcarriers. And then the users are actually moving within each cluster. And then the data set essentially provides channel data for 500 frames. And another data set that we're providing as part of this challenge is a high mobility data set. And this particular data set is created based on a channel simulator called Quadriga Channel Simulator. You see the link to that here. It's using a 3GPP model called the Urban Micro Line of Sight model. And 64 antenna base stations are used, and 64 users transmitting across 52 subcarriers. And the difference with the previous one is that we have higher mobility here, where the users are actually moving at random directions with a speed of 2.8 meters per second. And there's also 500 frames of channel data available in this data set as well. And then another resource that we're providing is actually the baseline code for the DRL-based scheduler that I talked about earlier. And the code is available in this GitHub repository. What this repository contains is a Python-based massive MIMO simulator, which is essentially the environment for the deep reinforcement learning, where you essentially get feedback from, you make decision on and get feedback from. And then there's also a Python and PyTorch in particular baseline model code for training for the baseline solution. So as we're going to essentially provide materials for this challenge on GitHub in this particular link, where the links to the low mobility and high mobility data sets are actually provided, as well as other resources and documentation material for the challenge. And then the baseline train model for this two data sets that I just talked about will be posted on this same link very soon. So this can be used by the participants to essentially kind of test their solutions and then compare their solution with the baseline model. And in the next step, I'm going to talk about the submission and evaluation and how we're going to evaluate this in this challenge, how we're going to evaluate the solutions. So the train models that the participants will submit will be essentially evaluated on 200 frames of data based on 3 metrics. One is the rate that I just talked about, so the average rate across all 200 frames. And then a fairness value, which is essentially the fairness that the network has provided across all users based on this Jane Fairness Index that I just talked about. And lastly, based on the runtime of the train model, right? So how long it takes to run the train model on the data for 200 frames. And then what we're using here to evaluate the solution is based on a variation of the provided data sets with different parameters. Same parameters, that means the same number of antennas, same number of users, same number of subcarriers, but just the channels will be slightly different. And then for the submission format and rules, essentially you will be providing your train model with code, you're submitting them, and then the way we're going to evaluate them will be based on essentially this table. We're going to use this rubric to calculate a score. So essentially, there are 6 metrics here across 2 data sets, low mobility and high mobility, sum rate, fairness, and runtime for each data set. And then the rule here is that the submitted model should essentially beat the baseline in at least 1 out of the 6 metrics. And then essentially you see here that we're going to essentially use this rubric, but then let's say this RS is the average of the low mobility and high mobility, right, results as well. And eventually we're going to give 40% to the rate, 20% to the fairness, and 40% to the runtime of the algorithm. So in this case, runtime will have essentially a very high importance here as well. And lastly, I have to mention that the updated baseline numbers will be essentially posted on the challenge repository, GitHub repository, in the link that I provided earlier. The timeline, the start date, I think it's already started, but let's say today is the start. End date will be August 9. And then a week after, we're going to essentially go through the evaluation. On August 16, we're going to essentially announce the rankings. The prizes will be 1,000 Swiss francs that is announced already. And also, we're going to have internship opportunities at Rice Wireless for the winners of the, or research visits, essentially, for the winners of the challenge. So that brings me to the end of slides. So these are the few links that you might want to look at. And then for questions, please feel free to email me or my student, Ching An, these email addresses. So I'm going to hand back to Vishnu.
Great. Thank you. Thank you, Ashu and colleagues. That's a great problem statement. In fact, I remember the long discussions that we had. So thank you for coming, with the well prepared data set, and we appreciate the effort put in collecting the data set. I was looking at the notes as you were speaking, and it goes back to 2022, I think. So that's long. That's a long time that we have been discussing, and I'm sure you were busy collecting the data set and validating it. Thank you so much for the efforts. First question about there is something here. So Abdul Qadir is asking, baseline solution paper assumes 20 megahertz spectrum with B resource blocks. I want to ask if there is a limit on number of users assigned to an RB, or maximum RBs a user can be allotted to. How Nmax is determined at each time slot. Do you want to take that?
So I think the maximum number that theoretically can be used, let's say 64 base station antenna is 64. So technically you should be able to maybe beamform to 64 users, but you get diminishing return because of this inter-user interference. And that's the job of the algorithm, to find essentially the right number of users to beamform to in each transmission period.
So in short, that is part of the design parameter, and it's dynamically chosen based on the channel conditions. So there is no hard limit from us.
Great. Yeah, that's what I was going to ask. So there is no hard limit from your side.
Right.
Each time slot, is there something that you need to answer about the last part? How Nmax is determined at each time slot?
I think Nmax is the number of users allocated in each time slot, and that is also not hard. The hard limit is 64 antennas, is based on 64 is 64. So, and then the number of slots each user can get is also determined by the algorithm. So it's scheduling how many users are in each time slot, time frequency resource block, how many slots are allocated to each users. And because each choice impacts the rate on one hand and also fairness on the other hand. And so there is this push and pull between the two things. And that is basically what the role of the algorithm is, to figure out what's that sweet spot we can get, push the rates, but also keep a high fairness and keep this balance.
Yeah,
very good. Thank you.
Very quickly add to that. I'm not sure if it was addressed or not. So part of the question is there a maximum RB a user can be allocated to? That's also no. There's no maximum on either side.
Yeah, they can be in all 200 RBs for this computation, if that's the right thing to do in this case.
Mm-hmm.
Great. Okay. Thank you. So I had, while we wait for the other questions to come, I had a question on the runtime. So in one of your slides, you had mentioned challenge evaluation metrics, and one of them was runtime. I was wondering how you would measure it, or how one should measure it. In this case, because it would matter when you start the clock and stop the clock, and what would you say? Do you have some recommendations on how one should?
Raymond, do you want to take that?
So yeah, sure. So I think the baseline solution will essentially include like a mechanism to measure the runtime. For example, let's say there's a command to start the clock, and then there's the code, and then a command to stop the clock. So essentially, the solution could use the same method, just replace the algorithm in between, and then measure the runtime on their end. So I guess runtime is something that depends on the kind of computer that you're running on as well. But you can run both the baseline solution and your solution on your computer, and then kind of decide whether you make an improvement there as well. And then we're going to essentially do that on our end as well. When we're evaluating, we're going to use a certain machine to essentially do this measurement, and then we're going to evaluate accordingly.
Okay, thank you. Hashem is asking, the model is a reinforcement learning model, so we just need to change the deep network of it. Okay, yeah.
Okay, so I mean, in principle, so let's see, right? So indeed, the baseline model is based on deep reinforcement learning, right? So it's a reinforcement learning architecture, or reinforcement learning model based on a neural architecture. You know, here the participants can get into the baseline they want and use that to start and build on top of it. And, you know, part of it could be to change the architecture. So this is valid. Is it not true that that's the only thing that you can do, right? At the end of the day, how you decide which users to allocate based on the channel, you know, is you can do it however you want, right? So you can look at the stars and decide, and that's it, right? So it's probably not going to work well, but we are completely agnostic to what you end up wanting to do. Indeed, you know, maybe starting from the baseline and trying to build on top of it could be a way to start with relatively safe grounds, and then based on what you get from that, explore further. That would be my recommendation.
Great. Okay, thank you. I have a little breathing space. That means I'm going to fire another of my questions about the user distribution. So you mentioned high mobility data set. I mean, in the high mobility data set. In the low mobility data set, you have another distribution. So can you explain like what the participant should use from both, or there is a distribution between them, or what is the distribution between the challenge data sets? Should the training be done for both, or what should they do?
So I think the training can be done on both data sets, right? They're free to use both data sets, or essentially one data set if they wish that. But then the evaluation would be essentially done on both, right? On both cases. So yeah.
That makes a difference. All right, that answers the question. Yeah, thank you very much. Let me see. Okay, so that means I have one more shot at it. Let me see. I think there was this question of deep reinforcement learning. Whenever I talk about deep reinforcement learning in relation to scheduler, the first question that I am asked is latency. So I think your runtime kind of answer that question, but I want to ask in general. What is the future of deep reinforcement learning with respect to scheduling? The reason I know the time constraints, that's why I'm asking, would this fit as one of the algorithms which is possible to be done in a commercial scheduler at all? Is that the holy grail, or is there something else that one should be looking at?
I think yes. I mean, I would say yes, it can be used. In fact, I'm aware of some companies that they're looking into this, right? So essentially, the deep reinforcement learning in particular can be considering a lot more parameters within a 5G stack as well, and not only the channel. So, but for this challenge, we have only focused on the channel itself. But as you can imagine, if you increase the number of parameters in the system, things can actually get a lot messier and harder to essentially come up with a good algorithm that works well. And I think that's where there's a lot of opportunity for using machine learning, in particular deep reinforcement learning, to do a good job here. That will be my answer. I don't know if Ashu and Santiago want to chime in here.
Yeah, I mean, the only thing I would add to that is, and maybe Vishnu, you were referring to this, right? So, you know, deep reinforcement learning in general can be a little bit data hungry on the training side. So if we're on setups where, you know, the channels can change and that's fine, but somewhat the distribution shift is not that severe, then you can gather, you know, the data that you want, train it, and then during implementation itself, you know, your agent can be based on a new architecture, but not too complicated either, right? So that the latency during inference time might not be that large, right? Of course, if you need to retrain when you have distribution shifts, that's where things get, I think, more tricky. So part of the real life implementation, which goes a little beyond. So here we talk about two setups, you know, low and high mobility. Of course, in reality, you have way more than that and things in between, etc. So I think a big challenge towards real life implementation would be on the robustness of the system and their how they adapt to distribution shifts. Again, this is maybe partially addressed in part of this challenge because we're looking at two setups, but in reality, we'll have maybe a continuous distribution shift, and that would be one of the things that we need to overcome.
Yeah, I think that's an important point. It's actually quite interesting that you guys are you guys not bothered about the memory footprint at all, or is that something which is not bothering you? Because I think in the scheduler space, it's quite tight. I mean, the budgets, the memory budgets that we have should be quite tight, no? Maybe in future, is it? What kind of so let me ask two questions. One, what kind of memory budgets do you guys see? And second question is baseline results. I mean, even for runtime, do they look? How do they look? Are you guys publishing that at all? Am I asking wrong? I should not ask confidential questions. So, you guys are publishing that, or is that secret information, or baseline memory footprint and runtime information? Are you publishing that?
Yeah, we definitely publish the baseline on our end, with the kind of machine that we run on. And yeah, so essentially we're going to use the same setup, same environment to essentially measure the solutions as well, right?
And then sorry, Rahman, the paper which Rahman cited does have results on runtime. I think Vishnu, maybe were you asking publishing like in a journal or a conference, or publishing for the, I assume you mean both. And then, so we do publish those results, and computational complexity is really crucial in scheduling, because that is the key problem to address. The optimal is known, but optimal is just NP hard. So
Yeah. No, I think I was just asking whether your baseline results are out. I mean, it could be published in your paper, or it could be you could just put it in the website. That's fine. So
yeah,
the answer.
Yeah, so we have some numbers that Ashu mentioned in the paper, but these are for the particular data sets that were used in the paper. For the data sets that we provide for this challenge, in the next week or 10 days, we're going to be posting all of that on the GitHub repository, so everyone have a reference point. Yeah.
Great. Yeah. Thank you. I'm quite interested to see that. Israel is asking the same question that similar question that I was asking earlier. Are you aware of any 5G commercial system using AI-based scheduler?
I'm not. So mainly because most companies, they don't tell you about what they're developing. But I know that there's a lot of interest in the context of VRANs, particularly when we talk about virtualized RANs, software-based RANs. that opens up opportunities for essentially bringing AI into software and open source software. So there are a lot of research going on, and particularly R&D, research and development companies, to essentially experiment with these machine learning based schedulers as well. So when that will essentially lead into an actual product, I don't have an answer at this point. But I know that a lot of R&D is going into this, and in the next maybe year or two, maybe we'll see something like that.
Great. Yeah, thank you so much. Yeah, I think open source is a good reflection of reality. So, yeah, thank you so much. Tian is asking, could you please explain the action space? Can we change the design of state and action?
I think the short answer is yes, and that the design is up to you all. So we're providing a baseline code and the baseline method, but no one has to stick to it. I think that's just a starting point as a reference point for those. So I think people get to design their own methodology to come up with solutions. Yeah.
Yeah.
You're
So
quite
just
generous,
to
actually.
add
Yeah.
on to that, sorry. So the action space, essentially the output of what we're asking of this model is indeed the schedule, like which user to schedule that in which resource block, right? So that you need to get whatever model needs to answer that. What they use as their state, right? Of course, you have the history up to that point, right? You could I only look at this channel, or you do an augmented state and look at the history, you look at the current rates of whatever of your users, etc. That part is indeed for you to design, right? So how large or small you want your states to be, and then how you design your policy, right? So you're mapping from state into action space, how you parameterize this policy, or how, again, whatever you do to map states into action, that's absolutely up to you. Then we'll just grab that little box that maps states into actions, put it into our evaluation and see how it compares with the rest.
I see. Okay. Thank you so much. Let's move to Walter. Do you see any kind of application of LLMs? Okay. Yeah. So LLMs in this field, please.
Yeah. So I haven't seen any, right? So a lot of the LLM things that I've seen within networking is more on the interaction side, with some sort of user, and then they would call something in the background, right? So something like, you would, in terms of natural language, communicate with an LLM, that then this could be calling some model in the background that tries to, solve the scheduling, running some of these DRL or whatever other procedure. The foundational model LLM kind of directly acting on the problem, that's something I haven't seen. Yeah.
Yeah, you're right, Santiago. I mean, we haven't seen either. I think there is some use cases for a generation of data that we have seen, but that's not very directly answering this question.
Yes, that's a good point, right? So having foundational models, not necessarily text-based, but the idea of foundational models as generative AI, and then using those for realistic data generation that is then used to train something hungry, like a reinforcement learning model. That could be a good synergy between these two ways of thinking about the problem. Yes.
Gary is asking the question which we normally get, that is outside data sets, which I mean, exactly like what we discussed just now. Can we generate our own data sets to augment the training?
Yes, I think, go ahead.
Yeah, so we were discussing this with the team before, because we thought we were gonna get this question, and there were some back and forth, but I think we landed on yes. So that will be our consensus answer, and that will be the accepted answer for the challenge. Yes.
Cool. I mean, you guys are the most generous host that I have seen. Yeah, thank you so much. I think you're basically allowing pretty much a lot of flexibility. That I think that's a longer term view to look at. Let me look at Asma's. Yes, I think this is an interesting question, especially for students. What's the size of the data set? Whether it will fit in my PC. I mean, that's not here. For each scenario, low mobility or high mobility, what's the size of the data set?
I think the size is not huge. I think each one is like around 1 gigabyte, if I'm not mistaken. Yeah. In that range. Yeah.
Very good. So that gives me a little breathing space to ask some of my questions. Maybe another couple of minutes. Let me just see my list. So fairness, yeah, I think that's another tough metric. Can you explain your metric a little bit? I mean, how did you come up with this metric, and why so? How does it reflect this fairness, please?
So the fairness is actually kind of have a very well-known metric for it, right? It's called Jane's Fairness Index. And essentially, and if you actually look at the baseline code, you can actually find a piece of code that calculates it for you. So you don't have to reinvent it. So I think everyone should stick to that. And then essentially, it measures how it measures how fair you are to all of the users. So for example, what you can do is that, let's say maybe there are some of the users are always in a bad spot and experiencing very like bad channel. So essentially, if you're just trying to maximize your rate, you never give a chance to those users, right? So you keep beamforming to the users that are in good channel environments, and then you get a maximum rate, but then your fairness metric will be very low, right? So we want to avoid that in real scenarios, obviously. So that's why we're using this particular Jane's Fairness Index is actually widely used. So we're gonna use that as well here. And we can use again, the baseline code to calculate that. You just feed in the rates that you're getting for each particular, let's say, subcarrier or transmission, let's say, case, like period. You feed it in that, and then it will give you the fairness value. And that's why we particularly use that in the reward function for the DRL, right? So that's one of the parameters in the reward function to be able to also optimize for that. So hopefully go ahead.
So just to expand the discussion on fairness, and this is a competition on machine learning, and the word fairness appears here. Kind of just to make sure, like this use of fairness is different from the idea of fair ML, right? So where you want your prediction to be orthogonal or agnostic to some features, etc. In those cases, sometimes you're trading off performance with fairness. I mean, sometimes you can win in both, but sometimes you're kind of trading off between these two. In this case, if you don't include some notion of fairness in your objective, then the result would be unrealistic. So it wouldn't be applicable in practice, just because of Raman was saying, right? If you just try to maximize, some rates, then that might be just, you always choose the better, the users with the better channels, and then the users with bad channels wouldn't be able to transmit. And for a real scenario, that wouldn't be the right thing to do, right? So here fairness is a very practical consideration, and some notion of fairness, or minimum quality of service, or however you want to put it, but some notion of that must be embedded in the problem, and this is how we decided to include it. Thanks.
Thank you. Yeah, I think that's a good clarification. I think anybody might actually get carried away by fairness. I think this is scheduler fairness. Thank you so much. Are you publishing a README file for a baseline solution and script on computing achievable rates, Jane's fairness achieved by the baseline solution? So basically, the question is on documentation and pointers to what we can reuse from the baseline code.
Yeah, absolutely. In fact, I don't know if anyone will see. I guess if I put it in the chat, no one will see that, right? So, okay, so yeah, I think there is a GitHub repository, as I mentioned in the slides. There is a README, but again, it's work in progress, right? So essentially, as I said, in the next week or two, we're going to essentially put even the baseline numbers. The baseline code is there. The link to the data sets is there in that README and the GitHub repository. And more information is to come on that README for sure.
Thank you. This is the Smart Scheduler GitHub that you're referring to, Raman?
Yes. But then there's a folder there called ML Challenge. So everything about this challenge we posted there.
Great. So what we will, if you put it on the chat window, our colleagues will carry it to the neural network forum. So yeah,
okay.
Thank you. Yeah, thank you. Gary, are there ongoing efforts to include modeling of different traffic demand usage from different scenarios? Yes, I think this is a good question. Apart from mobility, there are other parameters. Yes.
Yeah, I think for this particular challenge, we have not included the traffic, as obviously that's a very important metric for any scheduler to consider. So maybe in the next challenges we'll introduce that. But yeah, for this particular challenge, we're going to assume that there is essentially a full buffer for all users, right? So you essentially have to just look at the challenge channel and then come up with the best sort of allocation of users. The fairness metric is kind of like taking care of that to some extent, but again, in the case that we have full buffer users as well, right? So we want to make sure that every user gets an opportunity to transmit, but we don't particularly look at the traffic, different traffic levels for each user here. Yeah.
Okay, great. Yeah, thank you so much. I think we are having a great conversation, but Shozu is here. That's my cue to stop. So thank you so much. From my side, it's a great pleasure talking to you all. Thank you for patiently answering all the questions. And I would like to thank for your efforts for putting this together. So back to you, Shozu.
Thank you. Thank you very much, Vishnu, for moderating the Q&A. At this point, I would like to thank everyone for sparing your valuable time to join the session today. I would like to also express my gratitude to our speakers, Astosh, Sahaval, Rahman Dus Mohammadi, Santiago, for their contributions. We have more sessions in the future. Please check the AI for Good program page for details. You can also interact with us and other participants on the Challenge Slack channel. We look forward to your future participation. Thank you for joining us and have a nice day.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much. Thank you.